Let's discuss another kind of PN junction diode, which is light emitting diode, also abbreviated as LEDs. For an LED, to understand its phenomena, let's first discuss about a general PN junction diode, how current flows, which we already discussed. Like we can see that in a PN junction diode, in a normal PN junction, we can say in forward bias, above knee voltage, current flows because in depletion layer, electrons from N side and holes from P side combine and constitute current. And this is the reason why in reverse bias no current flows, because electrons and holes are drifted away from the depletion layer. Here we can also state that when electrons and holes recombine in depletion layer, photons of energy equal to delta Eg, which is the Fermi energy gap, is released. We already discussed that a PN junction remains in thermal equilibrium because of generation and recombination of electron-hole pairs. But specifically in forward biasing of a PN junction, when current flows and electrons from conduction band drops to valence band and combines with the holes, in that situation these electrons will release a photon which is of energy equal to delta Eg, and the number of electron hole recombinations will be equal to number of photons emitted, as corresponding to each combination of electrons with the hole, one photon is generated. And for a specific element, if delta Eg is given of a specific value in electron volt, correspondingly the wavelength is emitted. Like if we talk for silicon, we know the value of delta Eg is equals to 1.14 electron volt. That implies if we talk about the wavelength of photon emitted, this wavelength can be written as Hc by delta Eg, because we know that photon energy is equals to Hc by lambda. So wavelength we can calculate by using the expression of energy. So here if we substitute the values of constant Hc and if delta Eg is given in electron volt, it can be written as 12423 by 1.14 electron volt, which is equals to 10,898 angstrom. And this is the wavelength which lies in infrared region. So this is not visible, because we know that the range of visible light is approximately from 4000 to 8000 angstrom. So here the wavelength emitted is in infrared region only. But say if we talk about a specific semiconductor, which is not in your syllabus, but just for an example I am taking up, for a gallium arsenide phosphide semiconductor if we talk, or for a gallium arsenide phosphide semiconductor if we construct a diode, then we can say for this particular semiconductor the value of Fermi energy gap is approximately 1.9 electron volt. And corresponding to this particular energy, when photons are emitted, the wavelength of emitted photon can be given as Hc by delta Eg, and in this situation the value will be 12423 divided by 1.9. On calculation it will give the value approximately 6538 angstrom, and this is the wavelength corresponding to green color of light in the waveguide, which is approximately the middle range of the visible colors. So here we can say when a diode is constructed by the gallium arsenide phosphide semiconductor as an intrinsic substrate, then in this situation, when current flows through the forward biasing zone, here we can state the wavelength of green color will be emitted from the junction, and this color is emitted. So such kind of diode which emits light wavelength from the depletion layer, these are called light emitting diodes. On the next sheet we'll see a realistic situation how a light emitting diode works. Dear students, let's discuss a realistic situation how a light emitting diode works. Here this picture shows you a light emitting diode, and it is basically a semiconductor junction. We can zoom it and see, which is enveloped by a transparent polymer shell, and when it is connected through a battery in a forward bias mode. And here you can see a realistic LED has two terminals. One is short in length, other is large in length. The shorter one is connected to the N side of the junction, and the longer one is connected to the P side of the junction. Now when the switch is closed, you can see it starts glowing with a green light. And if we just zoom into the LED, we can see that there is a PN junction from which through its depletion layer continuously green light is being emitted, and it is because of continuous recombination of electrons with the holes in the depletion layer. As in forward biasing, these recombinations continuously take place, and corresponding to each combination of an electron with a hole, one photon of green light is emitted. So here we can say continuous emission of green light takes place. Similarly, such semiconductors can be used to make LEDs in which the Fermi energy gap is of the order of specific energy, which corresponds to red light of wavelength or yellow light of wavelength or blue light of wavelength, and corresponding LEDs will glow in various colors. So this is the way how a light emitting diode works.